So these reactions, given alcohol, OH with single molecule, we are treating strong acid, the sulfuric acid. So first thing we expect is that this OH getting protonated, so lone pair, grab the proton, then we got oxonium ion sitting right there on this carbon, which can give, because the neutral water is a good leaving groups. When this leave, we're gonna leaving carbocation on that carbon, which is a secondary carbocation, right? The secondary carbocations are not the best, right? So if there's another position that the hydrogen can move, then yes, it could potentially make a rearrangement. Well, first thing is, we're going to talk about rearrangement later, but if somehow your primary carbocation, the secondary carbocation that initially produced, the solvent can pick up the proton in the adjacent position, yes, you're going to have a E1 product forms from that already. But the thing is, I think the rearrangements will be fast because the secondary carbocations are less stable than the tertiary carbocation. So these hydrogen on the tertiary center moves, that's a basic hydride shift. And you moving the carbocation on the tertiary position, more stable carbocation forms. So that's the reason I think this is a main carbocation in the reaction mixture. This carbocation have two adjacent hydrogen, one on the more substituted side, one on the less substituted side. Depending on which one getting absorbed by the water, you're going to have a double bond in a different position, right? We talked about that many times. If the water as a base, come pick up the hydrogen on these methyl groups, then you're going to have a double bonds between those two. If the water comes and pick up these hydrogen, then you're going to have a double bonds within the ring, dot products. So these are the three potential E1 elimination products. Actually, they all come at the same time. This is the one basically we just talked about. You can predict which one is going to be the major product. So out of those three, which one do you think is the major product? This one, that one, or this one, right? And then the major product probably will come from the majority of the carbocation. And then more stable carbocation should be the majority. So this is the most stable carbocation. And then the more substituted double bonds are more stable. So these are just di-substituted double bond. We got the 2 carbon chain here. And that double bond is a 1, 2, 3 carbon chain. So this is definitely more stable than the other one. So I would expect that would be the major product. And that one, the di-substituted one, but I think it's a minor to that because it is coming from the less stable carbocation that initially formed. It may form, but not the large amount. It will probably rearrange first. And then making those two, major and minor, but this I would say the minor of the minor stuff. It's kind of silly to talk about which of the even more minor, but that's my opinion. And then this is kind of a carbocation mechanism. Some of you are thinking that, what about the SN1 reaction? Yes, water will capture the carbocation. Definitely, we cannot prevent that reactions. Water capture this carbocation, make an OH there. But if that happens, this one just looks like that after deprotonation. So that's why you don't see SN1 products when you do this. Dehydration reactions, SN1 reaction definitely take place, but you're not seeing the product because of you will just put it back to the starting point. But this is not the only carbocation, right? This is not the only carbocation. What if it's after rearrangement? What if the water capture that? Then you're gonna get the OH in the different places. Should we see this as a reaction, as a product? This is possible. The point is, you have to remember that the reaction condition is lots of protons available. That can be protonated too after it forms. When it gets protonated by the strong acid, then you're going to have a water molecule sitting on that. That will pop out. And then it's going to go back to the carbocation, which is the same as that. So in either way, as I said, one product is always going to put it back to a cycle, makes a carbocation. And then once it's dehydrated, there's no point of return. Product accumulated. So that's why you're never going to see SN1 products when you do the dehydration of the strong acid with an alcohol. It's not like they don't happen. They happen. But as soon as they make alcohol, it's going to go back to the dehydration again. So that's the reason why you can see alcohol is a product of the dehydration reactions. You only see the double bonds. Okay, so I hope that this answers. This shows you, what to do. To do more, let's say with a different alcohol, sulfuric acid. As I said, if it's an alcohol going for the dehydration reaction, you need acid. You don't treat the base with an alcohol. That's a different thing. You don't make a double bond with the base. With an alcohol. If you want to make a double bond with the base, you need to have aldehyde. That will make an acid, E2 or E1 reactions. But if you have an alcohol, you need acid. People confused about this thing so many times that are stressing out. The reactions are the same way. Hydroxyl groups get protonated, right? Then you got the water sitting right there. This pops out, then you got the primary carbocation, which is very bad. So this is not going to have a long lifetime. Immediately, it's trying to rearrange. And then thankfully, we got the carbon and the hydrogen on the tertiary center right next to it. So hydride shift is going to be almost automatic. It's pretty fast because the primary is very bad. So if it rearranges, then you got the carbocation, the tertiary center. Then this one has two different adjacent proton. Base, which is a water molecule, comes and pick up the proton. Depending on which one in the abstract, it will make a different double bonds. We pick up the hydrogen from the more substituted side, then you got the double bond more substituted. If you pick up the hydrogen on the less substituted side, you make a double bond with the less substituted. So you can imagine that would be the major product, this would be the minor product. And if you're somehow wondering, what if SN1 happened? I keep telling you, this will make the different alcohol, but that alcohol will be protonated, that alcohol will be protonated, and then going back to this point, so you're not going to see it. If this captured by that captured by the water, then it's going to go back to starting point. So you're not going to see the alcohol at all. You're only going to see the double bonds. Same thing with a different example here. There is an alcohol there using sulfuric acid. That will be protonated. Then we're expecting the water pops out. Leave a carbocation of the secondary positions. Then you need to analyze if this carbocation is going to rearrange or not. Sometimes it doesn't if there's a more stable one. But this was a secondary carbocation. We got a tertiary center right next to it. So that hydrogen, the tertiary carbon, make a shift. That makes a tertiary carbon being positively charged. And that's the one that's going for the E1 elimination reaction as a major species. So we got, again, two different hydrogen here. The hydrogen on the more substituted side, hydrogen with the less substituted side. Depending on which hydrogens are pulled by the base, you get different double bonds. If the base, which is a water, can pick up the hydrogen on this carbon, you're going to have a double bond there, which makes it 1, 2, 3, 1, 2, 3. Try substitute double bonds. If that hydrogen on the less substituted side, the methyl group is taken off by the base, then you're going to have a double bond right there. This is just 1, 2 substituted, disubstituted double bonds. So you can imagine this is a major product than the other one. SN1, there's another one possible, right? Because that carbocation, even though it's initially forms, potentially this can go to the E1 elimination and 2. It will make a double bonds in the different position, but I would say that's even minor products, right? Even that can make a more substituted product. So this one actually can be made two different pathways. Initial carbocation, somehow base can pick up this one, then you're going to make the same products. If it rearranges and then this pick up the proton, then you're going to make this one. So this one, that the major products actually produced by the two different pathway. So anytime that works, it just keeps accumulating So definitely it is a major product. And then this is silly. You're not going to see that as a one product because that is not you're going to be observing because as once you got the hydroxyl groups, you got so much sulfuric acid, it gets protonated, pops out. You're basically feeding back to the system, and it's going to be dehydration by the one. So that's what you don't see enough.